Welcome to Stat-ception, where I'm going to convince you that everything you think you know about statistics and psychology is wrong. So, my original title was a little bit different, but what we have been doing constitutes not statistics proper. If you went to a statistics department and said, hey, this is what we do t-tests and ANOVAs and correlations and stuff, they're going to be waiting for the and it's never going to come. So the stuff that we learn is not necessarily statistics proper. It's a very small subset of what statisticians actually do. So the bastardization of statistics is currently our practice in the field, but you can help science emerge victorious. So this is stats as we know it today. And by the way, the American Statistical Association has put out a statement about p-values. And this is from the introduction to that statement. Why do so many colleges and schools teach p equals 0.05? Well, because that's what the scientific community uses. Why does so many people still use p equals 0.05? Because that's what they were taught.
The matrix is everywhere. It is all around us. Even now, in this very room. You can see it when you look out your window or when you turn on your television. You can feel it when you go to work, when you go to church, when you pay your taxes. It is the world that has been pulled over your eyes to blind you from the truth. What truth? That you are a slave, Neo. Like everyone else, you were born into bondage, born into a prison that you cannot smell or taste or touch. A prison for your mind. Unfortunately, no one can be told what the Matrix is. You have to see it for yourself. This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more. Follow me.
So all the stats you've learned, t-tests, ANOVAs, correlation, regression, even chi-square, and advanced stuff like SEM. What if I told you that these are not part of science? What if I told you that they are distractions from science? Common statistical practice is the world that has been pulled over your eyes to blind you from the truth. Thank you. What truth? That you are a slave. Like everyone else, you are educated into bondage, educated into a prison that you cannot smell or taste or touch. A prison for your mind. So, ready to take the red pill? See just how deep the rabbit hole goes? Right. So, here's what some critics of statistical practice and psychology have said over the years. Stevens in 1960 called null hypothesis significance testing a meaningless ordeal of pedantic computations, which is about as savage of an attack as you can get in academia. And then so on, 60s, 70s, 80s. Here's from more recently in 2004. The routine use of linear multiple regression exemplifies another mindless use of statistics. You'll see a theme here that several of these people are calling NHST mindless. And so two economists, Stephen Ziliak and Deirdre McCloskey, wrote a book about this called The Cult of Statistical Significance. So from that book, they said, in a life in human sciences, a majority of scientists look at the world with what we have dubbed the sizeless stare of statistical significance. And they also tell us how big is a necessary question. It has no answer independent of the conversation of scientists, but at least has the advantage of being relevant to science, business, and life, whereas null hypothesis testing does not. And so I'm not going to read this whole thing, but their conclusion at the end, statistical significance of 5% or any other arbitrary cutoff level is neither necessary nor sufficient for proving discovery of a scientific or commercially relevant result. And so even the originator of this p equals 0.05 rule, Sir R.A. Fisher, wrote in the 1950s that this was based on a misapprehension, as he put it. So, what am I talking about? What is null hypothesis significance testing? Well, briefly put, you assume, depending on what question you're trying to answer, you assume there's no difference, no effect, no correlation. And then the second step is to look at the size of the mean difference or the size of the correlation, whatever it is that we're studying. And you want to see if that's significantly different from zero, given the sample size, given the amount of variability you see. And then you end up with a p-value taken from some table that was calculated many, many decades ago. And you compare it to the standard alpha level, 0.05. Sound familiar? So, if p is greater than 0.05, then this is your reaction. And if p is less than 0.05, then this is your reaction. So, I'll go through 5 of the major objections to null hypothesis significance testing today. I'm going to go into a little bit of depth, so we probably won't get to my solutions until next week. But next week I have a variety of slides that will help us tackle the goal of doing better science, of doing better statistical inference. So, for the first objection, Sir R.A. Fisher had the following perspective on p-values. He said that you should report the exact level of significance, that the p-value is a property of the data, and that he said the p equals 0.05 cutoff thing was just sort of a convenient guideline, but that it was flexible, and it's not some fixed thing that we have to do all the time. And I think, if I recall correctly, what Fisher wrote was that he takes 0.05 as a convenient guideline that if you don't reach that, he just sort of ignores the results. So he's not drawing any conclusions that, oh, there's no effect. He just says, well, I just sort of set it to the side. Then, statisticians Jerzy Neyman and Egon S. Pearson, son of Carl Pearson, for whom we know him from Pearson's R. So Neyman and Pearson instead advanced decision theory, which involves you set an alpha level, and once you set that alpha level, it's fixed. It cannot be changed once you get the data. And then you report only p is less than alpha or p is greater than alpha. And they saw p not as a property of the data, but as a property of the test itself. And so they went back and forth in a series of, again, pretty vicious academic arguments over whose approach was better justified. And so common practice as it's taught today is sort of a hybrid of these two approaches. We take pieces of the Neyman Pearson approach, and we take pieces of Fisher's approach and sort of smush them together. And then this is what we teach. So a lot of times, researchers do report the exact p-value. But sometimes, people actually do the p is less than 0.05 or p is less than 0.01 or whatever.
Point out,
Yes.
ever since I started graduate school, I was statistics, indicating exactly even how the issue.
So that's their, you're right, that's the APA's guidance, is to report exact p-values. I have, however, seen articles where they don't report the exact p-value, and I'm not just talking about like 40-year-old articles, I'm talking about more recent, like 10-year-old or less articles. And then what happens a lot of times is you will see an exact p-value that is then significant at the 0.05 level, or significant at the 0.01 level, or whatever. And so the point here is that what we normally do is sort of a Frankenstein's monster style hybrid. We've taken these pieces and put them together. And then what's worse is that we teach this as statistics per se. This is how statistics is done. When, as I alluded earlier, if you show this stuff to somebody in a statistics department, they're going to look at you like you've got 2 or 3 heads. So the first major objection is this incoherent hybrid approach. Fisher and Neyman and Pearson alike would say, this isn't what you should do, and this is what the field does. So the second major objection, as many people have noted already, that this fixed level of 0.05 is silly and unscientific. So I will demonstrate this with some examples. So let's say you're measuring the height of plants today, and then you measure the height of those same plants next week after you water them and make sure they get some light and so forth. And you find, after running the analysis, that they are in fact significantly taller at the p is less than 0.05 level. So that means we have greater than 20-to-1 odds that this plant growth is just happen to randomly occur by chance, and that plants don't actually grow. But I've taken this second example from my own undergraduate statistics teacher. He said, so let's say I've developed a vaccine for AIDS. And so what do you do when you give somebody a vaccine? Does anybody know? Yeah. So you take a crippled or dead version of the disease itself, the virus or the bacteria or whatever, and then you inject that, and so the body learns to fight it off. Well, that doesn't work so well because HIV is a very, very resilient virus. But in any case, so let's say I've developed a new vaccine and I want to make sure it works. And so we measure the incidence rate of HIV in our patients before the vaccine, which is by definition 0% because we're giving it to people who aren't infected yet. And then we measure the incidence rate of HIV a week later in these same people, and we find that this rate is significantly higher at p is less than 0.05. So are these questions equally important? Are we okay with making a 5% risk of error in saying the plants grow? Sure. We're wrong when we heard. What? Wow.
So of course your statistics are going to be messed up if you don't do your own test.
Yeah. So it's just to illustrate the point that depending on the risk depending on who's hurt. If I make a mistake with the first one, let's say plants are growing when they're actually not, but if I make a mistake with the second one, what happens? People die. So why are we using the same alpha level for each study? So the third one, so you will probably note that this isn't necessarily a result of null hypothesis testing in particular, but it doesn't help. So if p is less than 0.05, we say, all right, we got publishable results. I can take this to a journal. And if p is greater than 0.05, nobody's going to publish it. So we don't, a lot of times we don't even submit. So what can happen here is if we test a bunch of things and we find that p is less than 0.05 and everything with p is less than 0.05 gets published, we're going to expect about 5% of our results to just be spurious findings. We're going to expect them, we're going to expect some proportion to be false. We've said, yep, there's actually something going on here when there isn't. But what happens when replication attempts aren't published? So if you find something and p was less than 0.05 and it gets published, and then I do the same thing, and I have a failed replication, so the effect goes in the opposite direction, or it is near zero, nobody's going to know about it because nobody's going to want to publish it, because it might be because there's no effect, or it might be that I did something wrong, or I'm drawing students from a different population, and so forth. So journal editors can't tease that out, so they just say, no, we're going to assume that you did something wrong. And so spurious findings stay in the literature, and people go to read more about it, and they don't know whether it's true or false. They don't know whether this is a spurious finding or not. And even if there's a successful replication, so I do what you did, and I find, yep, the effect is of similar size, what are the journal editors going to say?
It's been done.
Exactly. They're going to say, we already know that. It's been published. But that belies the certainty of the original evidence. We don't know if a particular study, even if p is less than 0.001, we don't know if this is a spurious effect. So, like I said a minute ago, this isn't entirely due to null hypothesis significance testing. This is a problem with the publication process. But the fact that we use this bright line 0.05 criterion, if it's over here, then yes, it's publishable. And if it's over here, no, it's not publishable. That's contributing to the problem. And I'm going to say this again, probably next week. Replications are absolutely crucial to doing science. If you get a splashy and exciting new finding, well, that's great for when you make a press release for the popular press, because they can say, hey, psychologists found this exciting new thing. But frankly, we don't necessarily know that until the effect is replicated. Replications are a foundational part of scientific methodology. Inferences based on p-values are not. Yes?
How many replications do you need to conclude this?
That's a good question, and I'm going to give you probably more of a Bayesian answer. So here I have successful replications increase confidence in the presence and direction of an effect, and unsuccessful replications decrease our confidence or make us more uncertain. So as far as I'm aware, there's no standard about how many replications it takes. But, so I'll use my water bottle for an example here. What happens if I let go? It's going to fall to the ground. What happens if I let go? Yes, it'll fall to the ground if I don't catch it first. what happens if this falls to the ground? So the point is, gravity, as an example. We can expect the same thing to happen over and over and over again. Things are going to fall, if it's in a vacuum with no air resistance, things are going to fall at a rate of 9.8 meters per second squared towards the ground, towards the center of the Earth. Obviously, effects in psychology aren't going to be quite that consistent or quite that large necessarily. But if you have an original effect and you replicate it once, now I can be more confident that the first result wasn't just a fluke. If we do it 5 times, now we can be quite confident that the original finding wasn't a fluke. If we do it 10 times, we can be extremely confident. So yeah, that's ideally more replications are better, but up to a certain point, you get diminishing marginal returns. So Chris brought up meta-analyses, and that's helpful for doing better science, but it's not what we might want, because typically when we do a meta-analysis, we look at this published study and then this published study, which hopefully tested the same concept, but did it differently or came from a different perspective. And then this study and that study and that study, and we look at these effect sizes and combine them. And so like I said, this is a step forward. But if you don't have any direct replications, again, it sort of calls into question each individual effect that we found in the literature, each original study. Maybe some of them are spurious. Maybe it only requires certain conditions. For every published finding, we don't necessarily know how many other people tried to do the same thing and maybe didn't get any results. So maybe we can do a meta-analysis of 10 studies, and there are 1,000 studies that never got published. So that's why I bring this up as a problem. And even though it's not NHST in particular, our current statistical practice doesn't help matters. Okay. The fourth one is a logical problem. So first, we set up a null hypothesis of no effect, no difference, or no correlation. And then we attempt to get statistical evidence that shows that that is false, or that that is very unlikely. This is a straw man fallacy. And if you don't know what a straw man fallacy is, it's when you take an argument that isn't what you're actually trying to attack, but it's something close or it's superficially similar, even though it's fundamentally different in some way, and then you attack that. So an example might be, you got 2 political candidates, and candidate A says, I think we should lessen the penalties on possession of illegal drugs, and goes on to substantiate his claim. And then candidate B says, aha, candidate A is soft on crime. He's proposing that we let convicted criminals run loose among the general populace. But that's not really engaging candidate A's argument, because candidate A is saying this particular thing is causing more problems than it's helping. And candidate B is saying, well, you're soft on crime. Maybe candidate A is tougher on crime in some aspects. So the straw man fallacy is when you're attacking an argument that isn't what you're actually trying to engage with.
What is the argument?
So, thank you, Dr. Anderson. Very good question. What we're actually trying to show is that a particular alternative or a particular explanation is what's going on, what's behind a certain observation. But what we're actually doing is we're saying, well, let's assume null is true. These results were unlikely to have occurred if the null is true, therefore my alternative is correct. But these are not the same. Demonstrating that the null is false is different from providing support for your alternative. So even if the null is false, I'm saying, well, this happens because X, Y, Z, but maybe it's actually because A, B, C, or D, E, F, or G, H, I. We don't necessarily have any support, at least not statistically speaking, for my alternative versus a different alternative, or a different alternative, or a potentially infinite number of alternatives. So null hypothesis testing, as people like Jacob Cohen of Cohen's D have observed, null hypothesis testing does not tell us what we actually want to know. And we want so much to know that my alternative has some support that we convince ourselves that null hypothesis testing is the answer when it's not. And then number 5, I know Dr. Anderson has argued against this, but I can provide a list of references that argue exactly this point. There is rarely a difference or correlation among behavioral things or personality characteristics or whatever. There's rarely an effect of exactly 0 at the population level. And if this is in fact true, then 2 equal-sized effects, one might be significant at the alpha level of 0.05, and the other one is not, based only on the sample size. Even if the mean is the same in both studies, and the variance is the same in both studies, if one has a sample size of 20 and the other one has a sample size of 20,000, the one with the bigger sample is going to be significant, even for the same sized effect.
What does that have to do with zero?
So let's assume that at the population level, we're looking at a correlation of some personality characteristic, let's say your type A personality with IQ. So let's assume that there's not an exactly 0 correlation. Let's assume we got an R of 0.01 at the population level. Obviously, we can't know what's actually true at the population level without testing every single person. So the bigger your sample, the more, in fact, I'll show you mathematically. The bigger your sample, the smaller your p-value is going to get. So I'll show you with the independent samples t-test because it's pretty easy to demonstrate here. So does anybody know off the top of their head what the formula is for an independent samples t-test? No? All right. Well, I'm teaching stats this semester, so I know it off the top of my head. So that's the mean of your first group minus the mean of your second group divided by standard error. What's this? So standard error ends up being the variance s squared, that is standard deviation squared, of your first group over the number of people in the first group, plus s squared for your second group over n for your second group. Then you take the square root of all that. And I think that's the extent of the standard error formula. So let's put some numbers to make this a little more salient. So let's look at this. And the variance in the first group is 8, and then the sample size is 10. What do you get here? Yeah, you get 0.8 4/5. What happens if I get the same variance with a sample of 1,000? So 8 divided by 1,000 is?
0.00?
Yes, 0.008. So the point here is the bigger you make your sample, the smaller these numbers get. Ultimately, you take the square root, and so taking the square root of any real number, you will end up with a result that approaches 1, unless, of course, you're taking the square root of 1 itself, in which case you just have 1. But for any number that's not 1, you're going to approach 1, but it's not going to be exactly 1. So ultimately, the bigger your sample, the smaller your standard error gets. And then standard error goes in the denominator here. So if you hold the, for purposes of demonstration, if you hold the mean constant and you hold the variability constant, and you only change the sample size, you will get a number that's, you'll ultimately get a t-value that's bigger and bigger. And a big T corresponds to a big or a small p-value.
Since you're not holding the standard error, why would you hold the
So I've actually brought this up. So we can see this in action. Let's assume for a moment that we have 2 different groups. So I'm doing some intervention. Make up a story. So the mean for this first group is 50, and the mean for the second group is 49. This is true at the population level. Also true at the population level, we have an SD, let's see, I think it was 28. Right. So we have greater variability in the second group, but these numbers are constant at the population level. So now I take 2 different samples, and it just so happens that my 2 different samples perfectly reflect the population. In practice, that's obviously very unlikely to happen, but for purposes of demonstration. So I've got a sample of 200, 100 in each group. So I have GraphPad run the statistics, and I get a very small t-value, and the p-value is 0.8237. That's nowhere even remotely close to significant. So we'd ignore that result. So now, leaving everything the same except the sample size, now I get a much bigger sample, and I also get numbers that reflect the true population values. Now I end up with a p-value of 0.025. And the only thing I have changed is the sample size. So if Paul Meehl and David Lycan and Jacob Cohen and all the others are correct that we do have some, even if it's small, but ultimately non-zero effect at the population level, the bigger the sample, the smaller the p-value is going to get. And since p-values constitute, realistically, the criterion for whether something is worthy of getting published, p-values are being overweighted. So if I want to get published, I just need a big sample.
So what happens if you make 2 population means?
Well, if the 2 population means are exactly equal, then you're not going to find a significant difference, as far as I'm aware.
Which is what we're testing against. So
Yes.
basically, you're replicating the study 100 times, essentially, by increasing the sample size by 100 times, and then you're finding an effect where it exists. And that's bad.
Well, I will give you Jacob Cohen's words. So this is from a widely cited 1994 article by Jacob Cohen, the guy who invented Cohen's D, guy who was really big in power analysis and so forth. So you might not believe me, so let's see what he says. Cohen says, my work in power analysis led me to realize that the nil hypothesis, that is the hypothesis that there's exactly 0 effect, is always false. And then he goes on to quote himself from an earlier article where he says, if it, the nil hypothesis, is false, even to a tiny degree, it must be the case that a large enough sample will produce a significant result and lead to its rejection. And then later on in the article, he says, the notion that the correlation between arbitrarily paired trait variables will be of such minuscule size as to be of no importance is therefore incorrect. And here he's referring to a study published by or a theoretical paper, I should say, published by Meehl in 1990, where they did a survey of Minnesota high school students. And so they had an N of 57,000. And Meehl found when they did the variety of analyses to compare this variable to that variable, this variable to that variable, and so on. And they just did a bunch of correlations on all the stuff. And they found that, I believe it was 97% of them were significant at p is less than 0.05, and 78% of them were significant at p equals 0.00001, which indicates the impact of sample size on actual behavioral data. So the point here is that the result is unduly influenced if you have a really big sample. So you might be finding that there is, in fact, a real effect, but what you won't realize from looking at that p-value of 0.00001 is that the effect might not be worth considering, even if it's real at the population level. And so, to close out today, I'm going to refer back to Ziliak and McCloskey. So, why is sample size having such a big impact on p-values? It's because of what null hypothesis testing procedures actually test, which Ziliak and McCloskey point out is sampling precision. I think this argument is absolutely brilliant. Because what this tells us is, to use the independent samples t-test example again, so this is the difference between groups. So as long as this is not 0, I'll have a significant effect. This ultimately accounts for variability plus sample size. So we're looking at what's the difference between our two groups as a function of the variance. Well, the bigger you make a sample, generally we expect variance to be a little smaller or a little closer to the true population variance. But this difference here, the difference between means, unless you have some real weirdos in your small sample, you wouldn't expect that to change a whole lot. So ultimately, what we're finding is how much variance is measured by the standard error term. And then how big is the difference relative to that standard error, relative to that variance in sample size term. So that's all t tells us, is how precise is our sample, which the bigger the sample, the more precise the sample is going to be. We already know that. We don't need a test to tell us that. And so Ziliak and McCloskey's overarching point is that we're measuring sampling precision when what we actually should be concerned about is the practical significance of an effect. In social science, and they're economists, so obviously they're worried about policy decisions and so forth. This is true of any social science, really. We should be concerned about how much of an impact does this have. So if I'm going to put you through 12 weeks of therapy to cure your depression, we might have, if you get a really big sample to test my new procedure, we might have a significant remission in depression symptoms, but that's not necessarily going to be worth it if that significant remission is maybe 1 point on the 54-point BDI scale. That's probably not going to make somebody who's severely depressed jump to no longer depressed. So is it really worth the money and the effort for the treatment for very little change? That becomes less of a t-test or correlation sort of question and more of a, well, what's your priority? And that becomes more of an economic question ultimately. But I think they're absolutely right that sampling precision is not what we are looking for. What we are looking for is the impact of an effect. And so I also wanted to mention, so I created a data set to illustrate to illustrate an example that Ziliak and McCloskey used in their paper and also in their book. So let me bring it up here. So they use the example that, let's say your mom is trying to lose as much weight as possible, and she wants to do it with a diet pill, which has some negative health effects. But for this example, we don't care. We're trying to find the best diet pill for mom so that mom's happy. And so you ultimately arrive at 2 pills. Same price, same side effects. Everything is the same except for the effect of weight loss. So if you've got pill oomph, people lose an average of 20 pounds plus or minus 14. So people are, there's a lot of variability in how much weight people lose with pill oomph. With pill precision, we know much more precisely that people lose an average of 5 pounds. Some people lose 4.5, some people lose 5.5, but everybody's in that range. So I came up with a data set so that I could actually run the statistics and see what happened. So I used JASP here. And here's the result. So for pill precision, we have a 1-sample t-test tested against the mean of 0. And sure enough, there is a significant weight loss for pill precision. And then pill oomph, we also have a significant weight loss. But if you notice these t-values, the t-value is much, much bigger for the pill called precision, with a much more precise effect, but a smaller effect overall. And I was expecting to find, well, Cohen's d is an effect size measure. That'll fix the problem, right? Much to my surprise, it did not. And so I went back and looked at the formula, and Cohen's d is basically a t-test where you replace the standard error with the standard deviation. So here we just have 1 sample, so we wouldn't have to mess around with pooled SD or anything. We just take the standard deviation of the sample and insert that into the denominator. So ultimately, it's still a measure of precision. It's just not influenced at all by sample size. So in terms of interpreting Cohen's d, you'll see for pill oomph, this one, you'll see that Cohen's d is 1.43. That's pretty big. In social science research, that's a pretty big effect size. But pill precision has an absolutely monstrous Cohen's d value of 10. You will probably never see a Cohen's d that big in research, ever. So if you look at the null hypothesis significance testing procedures, you compare Cohen's d's, you would recommend pill precision to mom. That's the one where she loses 5 pounds, maybe 5.5, maybe 4.5. But as Ziliak and McCloskey wrote, mom doesn't want the precise effect. She's looking to lose weight, not to gain precision. And so ultimately, all you really have to do is look at the means and look at the standard deviation. Mom is basically certain to lose more weight if she picks pill oomph. But our traditional procedures would lead us to pick pill precision instead. So with that, I'll conclude today's lecture. Do we have questions?